So this is an example in SCT1 where the degrees of freedom in the p plus, p minus plane looked as follows. So we had hard modes that lived out here at p squared over some large scale q squared. Then we had collinear modes for the two jets that are going to be going back to back, and I'll draw the picture in a second. Then there were some ultrasoft modes as well that describe radiation between the jets. And then there can be also some lambda QCD modes, and we'll talk about them a bit today too. So there's a lot of different things going on here, but we'll see that actually we can understand everything and organize things using SCT. So what's the picture for these modes? We have back-to-back jets. Let me draw one jet this way, one jet this way. Maybe I should use some color. So there's one of our jets. There's another. And then there can be soft radiation. And between these jets, there can also be soft radiation physically within the jets, but there's no directional dependence to the soft radiation. So say that this is blue. This and this so far are orange in my picture. This is green. And then there's some hard interactions which we've already sort of localized into a dot in this picture. So what we're doing is we're colliding at E plus E minus, producing a virtual photon or Z, and then from that producing, if you like, a state which is full of collinear modes, state which is full of the other type of collinear modes, and ultrasoft particles. And this is in the center of mass frame. Or that's kind of how you could think about it in SCT. Or physically, what you're producing is you're producing jet 1 plus jet 2 plus soft radiation, or ultrasoft hadrons, soft hadrons. Okay, so the first scale that you want to think about is the hard scale. And so that is just the q squared of the virtual photon, or Z. So if you think about the Feynman diagram, here's E plus E minus, here's Q mu. You're going to have a pair of quarks that virtual particle can couple to, and there could be additional gluons. But the hard scale is set by the virtual photon, or Z. So there's going to be some scale associated to that hard scale Q. If you want to think about it as a renormalization scale, there'll be some scale where we want to match from QCD onto SCT, and that's going to be the hard scale. So I'll call that scale mu h. So then something physical has to set these other scales in the picture. And the next thing that we need to talk about is what we're going to measure. In principle, if you collide E plus E minus and you produce hadrons, you could have lots of different possibilities. In particular, you could have not dijets, but trijets. You could have a third jet emitted from a gluon. And some kind of measurement that we do on the final state is going to restrict us to this configuration with just two jets. And the one we'll talk about to start is what's called hemisphere invariant masses, which we already mentioned earlier. So the way that you should think about this is you take all the final state particles, you could just take the sum of all their momenta, and divide it into two parts. Those that are in hemisphere A and those that are in hemisphere B. So let me augment my figure here by saying that there's two hemispheres. And then what these masses are, which I'll call m squared and m bar squared, are just the 4 vectors squared for P for the A and the B guy. So written in terms of the individual particles in that hemisphere, you sum up all their 4 vectors for the particles in that hemisphere and square it. And then likewise for B. And if you're measuring these two things, we talked about earlier the fact that you could specify that it was a jet by demanding that they're small. So the Dijets is going to be m squared and m bar squared, much less than q squared. And if you had trijets, that wouldn't be the case. Because if you had trijets, you'd have two jets in this hemisphere at wide angles, and that wide angle would produce a large q squared, a large invariant mass squared m squared that's of order q squared. But if you just have a single jet, then you can have a small m squared. So the small m squared limit is what forces you to have dijets. And these guys here, and that also puts us in the kinematic situation where we have our n collinear modes for one jet and n bar collinear modes for the other jet. So those are two of the degrees of freedom in our picture. So I'm reminding you of some things we talked about before, but it was a while ago. So, and the power counting parameter here is m over q. And so if you want to say that there's a scale in this picture associated to the collinear modes, then you would say it's on a kind of jet scale, and that's of order m. OK. Any questions so far? So then there's the ultrasoft radiation. Which is, being ultrasoft, it's uniform. It's not collimated in any direction. It's the thing that gives you the communication between the jets. The jets are going to decouple from each other in the sense that interactions directly between the n collinear and n bar collinear modes is all going into the pink dot. But there can be long-distance communication between the jets caused by the ultrasoft modes. So really what I mean here is long-distance communication. Short-distance communication can happen too. That's what the pink dot is, but that's in some sense simpler. Long-distance communication can only happen by this ultrasoft radiation. And we know about how ultrasoft radiation interacts with energetic particles. And in particular, what we know is that it's iconal. That came out of our just Lagrangian description of ultrasoft radiation. And that will have implications here. So what is this ultrasoft radiation? It's radiation that has energy that's of order q lambda squared. And so that's m squared over q energy radiation. And so the soft scale, which is the next scale down in the picture, ultrasoft scale, is m squared over q. Often people will, because there's no soft radiation in this setup, sometimes people will just drop the ultra and just call it soft. That's very common. I'll try to always call it ultrasoft here because we'll be drawing some distinctions with SCT2 examples, and in those examples we have soft and collinear. In this example we have ultrasoft and collinear. So I'll keep trying to call it ultrasoft, but you can see that I've already abbreviated it to USoft to make it look more and more like soft. Anyway, but in the literature, people often just drop the U completely and call it soft. Something to be aware of. Okay, so this radiation here, this is the kind of the largest scale that can show up in the soft function. And there's also lambda QCD. And that's a scale that, at least to start, we're going to leave in the soft function. So if we go back to our picture over here, that's why I put both the ultrasoft mode that sat up on this hyperbola there, which is this m squared over q line, mu over m squared over q line. That's why I made it orange, and I also made orange this lambda QCD because they're together. And you can think of it as just that there's some modes that are capturing this entire region, which are the ultrasoft modes. Now, there are two, if m squared over q was of order lambda QCD, then those are the same thing. So there's kind of two possibilities here. You could have m squared over q of order lambda QCD. And that means that this scale is non-perturbative. And this is what's called, for reasons that will become apparent by the end of lecture, the peak region, because this is actually the region of the cross-section where there's a peak. Okay, that's why it's called the peak region. And in this region, you have the following hierarchy. You have mu h is much greater than mu j. Mu j is much greater than mu s, but mu s is of order lambda QCD. Okay, so if we take this to always be true, then we're in this situation. And there is another possibility, and that is that there's really a separation between these hyperbolas that's just as large or hierarchical as the previous separations. So if this thing is much bigger than lambda QCD, that's another possibility. And there'll be a region of phase space where this is true and a region of phase space where this is true. This second one is here at the soft, there is perturbative ultrasoft radiation. So you can just calculate it order by order in the ultrasoft scale, which is this scale, which is perturbative because it's much bigger than lambda QCD. And this is what's called the tail region. And the analog of this statement here is that we have a hierarchy between everybody. So when we do this analysis, what we're going to do is we're going to do a power expansion. And you can say, well, the power expansion is just what you told me, m squared over m squared much less than q squared. But you also have to worry about this when we're doing the power expansion. So one way of thinking about it is just exactly as I'm writing here, and that's how I want to advocate. The things you're expanding in are these assumptions. And you can see that in these two cases, there's slightly different setup. So usually when you have an effective theory, you have to define this from the beginning, because the way you proceed and how you set up your theory is going to depend on whether you're in this situation or this situation. But part of the story is the same in these two situations, namely the first two greater thans, much greater thans, are the same. And so that we can proceed without worrying about this. And then we can make this distinction later on, and that's what my picture was advocating for by having these guys be in the same category. So hopefully that's clear. Okay. So if you're in the tail region, there's going to be power corrections and these are actually the most important power corrections, that come as powers of lambda QCD over the soft scale. Okay? To some power, but you're going to have a power expansion in that. So that's the, if you like, in this situation where you're in the tail region, you can have power corrections that are non-perturbative by having ratios of these things, lambda QCD over this, over that, over this. But the biggest one are these guys over the soft scale. So that's the next smallest scale. So, but if you neglect these, the leading order cross-section in this region is perturbative. Now, you could have any power here. Those exist. What happens in the peak region is that thinking about those as an expansion is no longer good. And you have to take all of them and treat them as if they're order 1 and for any k. And that ends up meaning that there's going to be some non-perturbative function like a part-time distribution function in the sense that it's non-perturbative that describes part of what's going on here in this region. And that we just see from our power counting. I mean, our power counting already tells us that that's what's going to happen. So we can learn a lot just by thinking about the scales in the problem and thinking about the power counting. So you could ask about other power corrections. So there's a set of power corrections where you would expand in, say, mu s over mu j. And let me label these as kinematic, because the things that setting the scale for mu s and mu j, say in this picture where mu s is this, and I always distinguish lambda QCD as a separate thing, these scales are just perturbative scales, and they just correspond to, if you think about having some function that you're making an expansion of it. So they come about from expansion of kinematic variables, basically. So it's the m squared much less than q squared. That's what I mean. There's nothing non-perturbative about that. And then you could have power corrections that are lambda QCD over mu, which, if you like, are really hard power corrections. They're kind of the traditional power corrections, which are lambda QCD over the hard scale. And the exercise that I gave in the homework, in some sense, is going towards figuring out what the sort of soft function matrix elements would be part of the problem. There's other parts to it, but would be going towards figuring out what these guys actually are and defining them, which is not known in the literature. And then finally, you could have lambda QCD over mu j, which of course you could write. You have to be a little bit careful, because one way that this could happen is that you just have one of these guys times one of those guys. Okay, so it's not necessarily an independent category, but you could still think about these types of power corrections as kind of something that might show up either this way or maybe directly. And anyway, that's another category. It turns out that that you can get it this way, which is something that one can deal with. And if it happens directly, then it actually is down by two powers. So these guys are kind of less important. Okay, so people deal with these guys in the literature. These guys haven't really been fully treated yet. Not very much is known about them. And this is fully treated in the literature. These ones that I said are the most important ones. Okay, so we can already even outline kind of what people are doing because we just think about higher order terms in the expansion. And this is an example, unlike B to C decays where we had sort of people going to 4 orders down in the expansion, here even the first non-trivial order down hasn't really been done. Hasn't been done at all. In the second, there's various expansions, so it's more complicated, and some of them have been treated, but this one hasn't. And I should say that the way that this one is treated is really just perturbatively. So it's not, this one in some sense is also not treated fully in the language of the effective theory. It's just put in by hand. So in some sense, the only one that's treated properly is the top one. Okay, well, we're going to work mostly to leading order, and we're going to call these guys power corrections and work with this stuff.